Huawei Power Source is one of the leader and professional manufacturing in lead-acid battery in China and Thailand. From raw materials to end products are all made by our factory. BRLA batteries mainly used in backup supply, UPS, etc. Gel batteries are for the deep cycle, solar power, and wind energy. We also have full range of motorcycle battery, e-bike, and lawnmower battery. This is the location of our factories. International standard certificates guarantee our excellent quality. We are looking forward to seeing you in the fair.
There are many types of lead-acid batteries. While all lead-acid batteries have similar chemistry, each battery is optimized for a particular application. Let's have another look, this time in more detail, at the manufacture and assembly of a typical battery. Each plate group is made from a number of grids. The grids are stamped or molded from lead. As pure lead lacks the durability to withstand the rigors of automotive applications, various elements are added to the lead to improve its characteristics. For example, calcium can improve durability. Silver can improve conductivity. A paste of active material is applied to the grids. This is now called a plate. The active material on each plate is where the chemical reaction occurs. Once the battery has received its formation, the active material will consist of sponge lead for the negative plates and lead dioxide for the positive. Traditional batteries use a porous membrane called an envelope separator to separate the positive and negative plates. An AGM battery uses a glass mat to separate the plates. The plates are connected together by casting a solid lead attachment strap, the cast-on strap. This assembly is now known as a plate group. A plate group is inserted into each of the 6 chambers of the battery case. The plate groups are then connected by spot welding the cast-on straps together in series to form a 12-volt battery. The lid is then applied, sealed, and battery posts are connected. The chambers are filled with electrolyte and the battery receives the formation charge. As a result of the formation process, the chemical structure of the positive and negative plates has changed from a lead oxide compound to lead dioxide and sponge lead. The formation process chemically activates the battery and is critical to optimum battery performance. When the formation process is complete, the electrolyte now has a specific gravity of approximately 1.270. The battery is at 100% state of charge and is ready to be used.
Welcome to DECA University's Module 6, Understanding the Flat Plate Advantage over Tubular Design. There has been a lot of industry debate over which of these designs is better than the other. This module reviews the construction of both to demonstrate exactly how the DECA flat plate is superior to a tubular design battery. Battery grid design is key to battery power and life. Regardless of whether they are a flat plate or tubular construction, battery grids form the supporting structure within the battery and conduct power to the lugs, where it is harnessed to operate your lift truck equipment. Half the grids inside the battery are covered with lead dioxide to create positive plates, and the other half are covered with sponge lead to create negative plates. The positive and negative plates are grouped together with separators between them to prevent positive and negative plates from coming into contact with each other and creating an internal short circuit. Internal short circuits can result in battery damage, overheating, fire, or explosion. The grouped plates are fitted into a battery cell and filled with liquid electrolyte, which is a concentration of water and sulfuric acid. Individual battery cells are then placed together inside a tray to collectively form a battery. As a battery is discharged, the active material on the positive and negative plates react with the sulfuric acid in the electrolyte. Water is formed as a byproduct of this chemical reaction, which weakens the electrolyte solution. At a certain point, the sulfuric acid becomes too diluted for the chemical reaction to continue, and the battery is effectively discharged. The recharge cycle reverses the chemical reaction so that the plates release sulfate back into the electrolyte, which brings the battery back to full charge. One of the negative side effects of the recharge process is heat, which leads to battery gassing and water loss. Lost water must be replaced in order to keep the battery in good working order. At the most basic level, here are the most important things you need to remember about battery technology. Battery grid design is critical to battery power and life. The battery grid is responsible for conducting power to the lugs. If positive and negative plates were ever to touch, the resulting short circuit could lead to battery damage, overheating, fire, or explosion. The recharge process generates heat, which causes gassing and water loss. Lost water must be replaced regularly to keep the battery in good working order. The Deca flat plate grid design is composed of lead alloy wires which crisscross to create a network of squares. For example, a Deca 125 amp-hour plate has 224 squares. The spaces between these squares are filled with active material. If one of these wires were to corrode through, there are 3 other wires surrounding the square that can still conduct current. By comparison, a tubular plate design consists of lead spines enclosed within gauntlets, which hold active material against the spines. Unlike the Deca grid design, each spine has only one path to the lug. If the spine were to corrode through, there is no surrounding lead to continue carrying the current to the lug, and so all the capacity below the break would be lost. Since there are normally 15 spines in a plate, the corrosion of one spine can result in up to a 6% capacity loss. As the battery ages, it is possible for corrosion to occur on several spines, resulting in serious capacity loss and a reduction in service life. The amount of active material or paste contained in the battery plate is critical for both capacity and life. It is very important that the active material be consistently applied over the entire plate. If the density is too high, it will lower capacity, while if too low, it will cause shedding and early failure. At East Penn, the density of the active material is carefully controlled by computer-integrated paste mixing machines to predetermined values. The paste density and weight will also be very uniform when applied automatically by East Penn's computer-integrated pasting machines. For tubular designs, polyester tubes called gauntlets are filled with either dry or wet active material to create the individual tubes. The dry form uses a mixture of red lead and lead oxide powder while vibrating the plate to prevent the oxide powder mixture from clogging and assist in the flow. Alternatively, a slurry form of liquid and active material can also be used to fill the gauntlets. Both wet and dry methods can produce variation in density via the filling process, which results in an uneven discharge and charge of the active material that can lead to premature failure. In some cases, the extremely dense material can split the retaining gauntlet, resulting in severe shedding and major capacity loss. Grids are made from an alloy of lead. Some alloys use a small amount of antimony to strengthen the lead. This is necessary so the grids can be handled during the manufacturing process without being bent or damaged. Although an alloy like antimony is necessary to provide strength to the grid, too much antimony will increase gassing. More gassing means more frequent watering, which leads to more maintenance. Note that a tubular design relies on a higher percentage of antimony to add strength to its long, thin spines. The flat plate grid requires less antimony because of the natural strength and integrity of the grid-like structure. So as a general rule, flat plate grids will gas less than tubular grids. The retention system is a combination of material used to prevent active material on the positive plate from softening and shedding. An effective retention system is a sure way to help achieve long life. A Deca flat plate battery uses a multiple-step retention system. The first two retention steps wrap the positive plate with a vertical mat consisting of fiberglass tape and interwoven glass fibers. The glass fibers embed into the active material, strengthening in a way similar to reinforcing rods in concrete. A horizontal glass fiber mat is wrapped around the plate to break up any gas bubbles and increase the plate's insulation. The fully wrapped plate is then encased in a perforated plastic retainer envelope that firmly holds the glass wrap in contact with the plate, while allowing the free flow of electrolyte to have access to every part of the plate's surface. The separator is the last barrier between the positive and negative plate, protecting against shorts and corrosion. Deca flat plate cells also use a bottom plate shield to prevent sediment from bridging across the bottom of the plates and shorting out the cell. Tubular designs are limited to a two-step retention system, which consists of a gauntlet or tube of polyester fabric and a separator. Using only two methods for retention, a tubular construction is prone to more active material shedding. Loose active material floating free in the electrolyte can settle on the negative plate to create a spongy lead moss deposit, which could potentially cause a short between positive and negative plates, leading to premature battery failure. Another problem that can occur with limited retention is split tubes. Through excessive discharging and recharging, the active material can swell and increase pressure on the tube. A split tube results in catastrophic shedding, leading to significant capacity loss. A battery charger is designed to detect the battery voltage of the cells and use that voltage to bring the battery to full charge. When cells have equal voltages, charging will be more efficient, preventing gassing and sulfation, and therefore significantly extending the battery's overall life. To ensure equal voltages per cell, Deca motive power battery plates go through an extensive two-step formation charging process. First, Deca plates are individually formed in precision temperature and voltage controlled tanks, and each plate is then visually inspected to ensure it is completely formed. The process ensures maximum and uniform performance from every plate and ultimately each cell in terms of amp-hour capacity and cycle life. Second, the assembled cell goes through a boost charging phase where the cells are charged and optimized for long cycle use. As a result of the uniform formation of each plate, cell voltages are equalized and consistent, allowing for more efficient charging and therefore extended service life. Tubular manufacturers form the fully assembled cell after it has already been placed in the jar. There is therefore no way of inspecting the plates to evaluate the completeness of plate formation without tearing down the battery. This creates an environment more prone to unequal plate formation, leading to unequal cell-to-cell voltages, which is especially detrimental to the battery during the charging process. When cells have lower or higher voltages than the average charging voltage, those cells will continually be under or overcharged. Undercharged cells will build up sulfate on the plates that crystallize and cause parts of the plate to harden and become inactive. Overcharging cells will cause more heat and gassing, leading to more shedding and the need for increased watering. As you have seen, the Deca flat plate design offers significant advantages over tubular designs. The crisscross grid network of Deca battery grids provides alternative current conducting pathways in the event of grid corrosion. The computer-controlled paste mixing and pasting, possible only with a flat plate design, ensures more optimum levels of power-generating active material are consistently applied to every plate. Less antimony in the grids translates to less gassing, shedding, and watering. Deca's exclusive 5-step plate wrap process more effectively keeps active material on the battery plates so that useful battery life is extended. Tank formation and visual inspection ensure only optimally formed plates are used in the construction of Deca batteries. These distinct design advantages ensure that Deca batteries are built for the long run, providing the lowest cost of ownership in the industry. Thank you for viewing Module 6 of our Deca University, Understanding the Flat Plate Advantage over Tubular Design. Please see our additional training modules for information about our battery and charger lines.
Pollution Control Board KSPCB and Ministry of Environment and Forest MOEF. Battery braking machine. The scrap batteries are slowly fed into the battery braking machine and it is crushed in a staged manner. The first stage is the hydraulic crushing machine, where the batteries are cut into 4 pieces using a hydraulic press. The acid present in the batteries are collected in the tank present under the hydraulic crushing machine. The collected acid is processed in the effluent treatment plant by slowly mixing with it. The crushed batteries are carried to the next stage with the help of a conveyor. The second stage of the battery braking machine is the intelligence crusher. The broken pieces are further crushed into smaller pieces by using water as coolant medium. The smaller pieces are taken to the next stage with conveyor and the water is treated with effluent treatment plant. The third stage of the battery braking machine is the secondary crusher. The smaller pieces of batteries are mixture of plastic, lead and other ferrous metals which may be present in the terminals of the batteries. The ferrous metals are separated using magnetic separator and then again crushed into further smaller pieces using this secondary crusher. Water is used as a coolant medium during the battery crushing process and is treated with effluent treatment plant. The lead metal with the plastic mixer after this secondary crusher is collected in the hopper filled with water. The plastic with lesser density will float on top of the water in the hopper. The plastic is separated from the water by using the screening process and the lead metal collected at the bottom of the hopper is taken to the shaking table with the help of screw conveyor. The solid lead metal and lead powder are further separated in the shaking table by mixing with water. The lead metal is directly melted in the pot furnace and the lead powder is smelted in the rotary furnace. Effluent treatment plant. The ETP is designed for 8 KLT capacity in one shift operation. Equalization tank. The effluent washings from the process maximum quantity of 8 KLT will be gravitized into the proposed equalization tank for batch treatment. This tank has a storage volume of 3 days. The effluent will be further pumped out into the neutralization tank for batch treatment. pH is corrected by addition of lime. This tank will be fitted with mechanical flocculator with paddles, both for pH correction and to facilitate good floc formation. Here, coagulants like alum, polyelectrolytes are added to ensure good floc formation and lime for neutralization. The effluent will be further pumped out into the settling tank for settlement of precipitates. Pre-filterization tank, final pH adjustment tank. The overflow from the primary settling tank can be collected in a pre-filtered effluent sump of maximum 24 hours capacity, wherein the final treated effluent will be corrected for pH and is further pumped into a dual medium filter for further polishing the treated effluent and for removal of suspended solids and residual trace metals. The filled medium will separate any further solid present in the water. The final treated effluent will be pumped for distribution back into the process after blending with raw water if required as makeup water. The available retention time for holding effluent is around 3 days, hence adequate.
Up with it, girl. Rock with it, girl. Show them it, girl. With a bang bang. Bounce with it, girl. Dance with it, girl. Get with it, girl. With a bang bang.
Come on, turn the radio on. It's Friday night and I won't be long. Gotta do my hair.
Dance with it, girl. Get with it, girl.